We are now running the home stretch of this course, and we are going to do one last task for this second order ordinary differential equation, and that is to get rid of the dependency of knowing what that cycle was for the pendulum. So that was a thing we called cheating on the previous assignment because we had to use a bit of knowledge of the analytic solution to get our boundary conditions, and that's not so good. Instead, we're going to use initial conditions that will allow us to solve this problem without knowing the period. So let's give this a try and see if we can't get an improvement on our solution. We have the same formula here as we had before. We've already talked about this. We know these are for the interior points. We understand that each one of these equations involves three variables, which meant that we ended up with too few, in other words, two equations too few to solve the problem. You end up with n minus 1 equations only using the interior points, and you have n plus 1 unknowns that go from x0 up to x sub n. So we solved that problem last time by setting x0 equal to theta 0 and xn equal to minus theta 0. It's the second boundary condition that's problematic. The first one you don't need to know anything about the solution or the theoretic solution for this pendulum to say that the angle starts at theta 0. You observed that when you were starting off the pendulum. But you can't say that after n cycles or after n time periods that it has reached the opposite side unless you know something about the period. So instead, we would like to substitute that final boundary condition to one that involves the velocity. We know the speed at which the pendulum was going before we let go of the plumb bob. It was going 0. It wasn't moving at all. So we should be able to say that the first derivative of the angle with respect to time is 0. Now, can we create a formula that works with our discretized variables that still preserves the structure of the matrix or doesn't hurt it too much? So that's what we're about ready to do. We're going to see if we can still solve the problem, and we'll try to do it efficiently, but we will run into a little snag there that we will have to talk about. So let's consider this. Let's leave the initial position alone. Theta of 0 equals theta 0, but we'll add theta prime of 0 is equal to 0. So the thing is not moving. We need to come up with a numerical formula for a first derivative. Now, we had several of those that we used, actually two of them that we used in chapter 4. So let's go back and take a look at the structure that we have and see how we can create or modify these interior points using the velocity. So this is just a reminder. This is our interior points all laid out in our matrix. And we have a 1 over h squared here, which completes the derivative, but we don't really need it because all of these are set to 0, so you can multiply this whole matrix by h squared and it doesn't do a thing. How do we add the angular velocity into the missing rows? Well, let's suppose we go back to chapter 4 and redevelop the one-sided derivative. Okay, so let's just do it over again. Now, we've done this before in chapter 4. We're going to do it with our motivation that this is our underlying pendulum equation, but we'll set up our Taylor series again. This is review. You've already seen this in chapter 4. We set this x of t plus h equal to this nice form of the Taylor expansion that has powers of a constant being h. That was good. And we also recognize that if we subtracted x of t from both sides of the equation, we get something that looks very much like the numerator of a derivative. And if we then divide everything by h, we'll end up with x of t plus h minus x of t divided by h. Well, that's our classic one-sided derivative formula. And we'll get rid of one of the h's on every other term, which frees up x prime by itself. So we rearrange everything. We get a computational formula for x prime of t that looks like a first derivative that you had in calculus, but we have an error term associated with that. Well, what does that mean to our particular problem? Well, we know that if you're talking about x of t being maybe x0, then x of t plus h must be x1. Or if x of t is x1, then x of t plus h must be x2. So we could use the discretized values as easily as this form right here. So let's go ahead and try that. We'll plug in x1 for this x of t plus h and x0 for this one over here. And we'll set it equal to 0 because that's our, our initial condition. And we know that there's an error term associated with this. And now I'm a little nervous because going back to chapter 4, that was an order of h error, and everything else that we've got corresponding to the interior points on this pendulum are order of h squared. So I kind of don't like that very much, but let's see where this goes. And it turns out, if you check other literature, it's not always a disaster to do that. But in this case, it is going to create a problem because this equation here means that x1 must be equal to x0. The consequence of that is that the pendulum hasn't moved. I've said that my position after you've run a bit of time, the time is h, that x1 hasn't moved away from x0 at all because the difference of those two angles is 0. And I don't think I can live with that. That's introducing a error right from the get-go, and that's probably going to do the same problem we had with the Euler method of introducing a bias from the start. So I'm going to abandon this approach and see if we can come up with something better. So let's go back to our problem again and see how that issue could be corrected. Now I'm going to do something that looks really weird. We're going to introduce what we call phantom variables. So these are angles that won't ever exist, but we're going to use them as stand-in variables to see if we can do a little bit better on our numerical methods. The stand-in variable that I want to introduce is called x sub minus 1. There is no position for that. I don't have a angle at one point prior to time 0. I just don't have it. But no, it doesn't matter. I'm going to throw it in anyway. If I use my central difference approach to derivative, not the one-sided one, but the central derivative approach, then this turns into x1 being identical to this phantom variable x minus 1. But it doesn't say anything about it being equal to x0. So okay, let's try that. There's an equation. I could also continue to use it with my second order derivative. So if I plug in my phantom variable, the x0 as the middle value, and x1, then this equation must also be equal to 0. I now have 2 equations and 3 unknowns. Well, I think I can come up yet with another equation, and that is x0 equals theta 0. That's my initial condition. I know that's true. I now have 3 equations and 3 unknowns, one of which I'm not really interested in except just to complete the puzzle. Could this result in an x1 that produced a slightly modified matrix but did so only with initial conditions? And the answer is going to be it will. So let's just see what those 3 equations were. This is just copying them from the previous page. So I have x1 minus x minus 1 equals 0. We have the second derivative at x0 must be equal to 0. And we have x0 itself is equal to theta 0. Now we could go through and do the linear algebra and find the solutions of all that, but that's really a Math 341 problem, so let's not. And I think when you see the solution, you'll see it's pretty obvious that has to be it. I mean, x0 has to be theta 0. That's part of the solution. We know the difference between x1 and x minus 1 must be 0, so they must be the same. And they also have to be able to work on this middle equation, and that's the only set of values that will accomplish all 3 equations. So you can solve it by hand if you want, and you'll end up getting this solution. And now the question is, what can we do with it? Well, we don't really need x minus 1 anymore. Okay, that's not really part of the problem. We need to continue to use x0 equals theta 0, and now we will introduce this new requirement that x1 has to be this sort of complicated construction involving theta 0. How would that affect our matrix? Well, it doesn't change the beginning line. That's the same as we had before. It doesn't change all the interior lines. but it does modify the very last equation that we have. Instead of a 1 on the right and trying to specify something about x sub n that we don't really know, we can specify a criteria on x1 that we have now just calculated, knowing that the velocity has to be equal to 0. There's only one serious downside with this whole approach, and that is we just blew out of the water the tri-diagonal nature of the matrix. We've got this funny row down here that won't fit our algorithm's logic, and you won't get the right answer if you try to use the same algorithm that we did on the previous exercise. Well, you could say, well, I could move it. I mean, I could rearrange rows. I could stick this whole thing at the top, or I could stick it in the, somewhere near the top. And if I did that, I still blow away the tri-diagonal nature of the matrix. But if I did something like that with some fairly minor modifications to the code, well, not entirely minor, but sort of minor modifications to my previous homework, I could change the algorithm to account for the different sliding positions of these rows. And that would be a great exercise. I'd love to give you that to you as a homework, but I know we're at the end of the quarter and we're kind of getting into graduate level stuff, so I'm feeling guilty about that, so we won't do it. So I am going to instead commit the ultimate sin of this course and allow you to use a MATLAB function that I've never let you use before, but it is kind of a nice present for the end of the course. And besides that, when you start using MATLAB for real problems, you're going to use this all the time. And that is, if you're trying to solve the equation ax equals b, you can do so in MATLAB by just writing down x equals a backslash b, and MATLAB will come up with the best algorithm it can given what you've given it, and it'll solve the problem. So for your homework, you can go back and set this matrix up, by modifying the previous homework. Get rid of all the solutions you did, your Gaussian reduction, you can get rid of all that, and you can just substitute all that with this equation right here, and that will be permitted for our final homework in this course. But when you do it, in exchange for me making that a whole lot easier than it could have been, is I want you to answer some questions. The first thing I also want to mention is that when you choose your interval h, to pick the same h you used in homework 7.4a. Now you may say, well, that still requires me to know the period. Well, this homework would work regardless of what h you use, but I want you to use the same one so you can compare apples with apples and see that the result is just the same or virtually the same. So I want you to do that. I also want you to create enough rows initially to solve 5 full cycles. So you're going to have to think about how to modify your matrix so you go beyond just the half cycle, but you go to 5 full cycles. After you solve it, I want you to try it again. You've already done it at 5 cycles. I want you to try it again at 15 cycles. And I want you to ask yourself, did the program seem to work harder at getting that job done? And I need you to give me a reason for why it's slowed down quite a bit. You should notice that. Plot the thing on the result, and then I want you to tell me in words, not just part of your MATLAB, but write down something and send it to me. What are the serious flaws with this approach that really drive inefficiency into our program? You still got the right answer, but it's inefficient for 2 very big reasons, and I want you to explain what those 2 big reasons are. So with that, have a wonderful vacation. I hope this course has been helpful. If you ever choose to take more numerical analysis, there's some really good courses at most universities, particularly at the University of Washington Applied Math Department, and it's some pretty good stuff. So have a great holiday.